Hi class, it's me, Mr. Morris, and this is a video with a couple example problems where you're looking for the percent abundance. And as the last video told you, this is a little more tricky than just finding the atomic mass of an element, but it's not too bad. I want to show you my way of thinking about this and how that you can set up a table that will help you to solve these problems. It's a good way to show your work, and it's a good way to keep yourself from making some of the common mistakes. So first, let's read the problem. Calculate the percent abundance of copper 63 and 65. Pay attention to the words. It wants the percent abundance, so at the end we're going to have to make sure we convert to percent. And it tells us if the atomic mass is 63.546 AMU, that is our atomic mass. Remember, that means it's the average. Our atomic mass is the abundance of the first element, or the first isotope, times the mass of the first isotope, plus the abundance of the second isotope, times the mass of the second isotope. And if I have 3, then it would be plus the abundance of the third isotope, times the mass of the third isotope, and it goes on and on, however many isotopes you've got. All right, so percent abundance, if the atomic mass is 63.546 AMU, and the exact masses of the isotopes are, and it tells us, we have copper 63, has a mass of 62.93 AMU, and the mass of copper 65 is 64.93 AMU. We're assuming that no other isotope exists. That's important because if another isotope existed, it would throw this off. But we know that those are the only two. So first, let's make a table with the data that we have about these two different atoms. So I'm going to make a table that's copper 63, then I have copper 65. All right, and in the middle we're going to put the abundance, and on the other side we're going to put the mass. All right, so we have the mass of copper 63 as 62.93 AMU. The abundance is unknown, so I'm just going to call that X. Then I have copper 65 has a mass of, we just said 64.93 AMU, and our other abundance, we could call it Y. So just a reminder for you, that Y isn't going to help me much because it's awfully hard to do math with two different variables and you don't know what either of them are. So what we want to do is replace Y with something to do with X. And we know that X and Y, those are abundances, which is like a percent turned into a decimal. So if these are the only two isotopes, then if we added up their percents, they would have to add up to be 100%. And if that means if we added their decimals up, their abundance up, they would have to add up to be 1. So I could tell you that Y equals 1 minus X, and that's an important fact we're going to use. 1 minus X. That's the way we're going to plug it into our equation. All right. The other thing we need to know is the atomic mass. We've got this formula up here that's really useful, and atomic mass is given to us right here. So we're going to start with that. 63.546 AMU is our atomic mass, is equal to abundance 1 times mass of isotope 1. Well, abundance 1, the abundance of copper 63, is X. So X times the mass, 62.93, plus the abundance the second abundance, which was y, but we called it 1 minus x times the mass of copper 65, which is 64.93. So that's the formula. I know the atomic mass. My unknowns are x and 1 minus x. So now we just want to set it up and distribute. Doing this algebraically, your first step is going to be distribution. Well, I'm going to rewrite this the same way it was because I didn't change 63.546. And then it equals x times 62.93. A nicer way of writing that is 62.93x plus, over here I have 1 minus x times 64.93. Well, if I distribute that, 64.93 times 1 is 64.93. And then it's 1 minus x, so that's a negative x. I'm going to have to put minus x times 64.93 is just 64.93x. All right, so we distributed. Thinking back to your algebra skills, the next thing you do after you distribute is you combine like terms. So combining like terms, I'm just going to switch color really quickly with this pencil. Let's make it red. And we're going to be combining like terms. So the x term needs to combine with the other x term. And then the term that's not x, it's just a number, needs to combine with the other number. And since we're switching sides, we're going to switch sign. So back to what we were doing, 63.546 minus 64.93 is negative 1.384. And technically, because I have two decimal places in one of those two numbers, I should round to 2 decimal places. So really I should put negative 1.38, and that should be my answer. I round it just to 2 decimal places. Now, I will tell you right now, I in particular am not picky about sig figs on isotope abundance, but technically that's what you should do. And then we're going to do this red term that I have here, the x terms. We're going to combine those terms, which means 62.93x minus 64.93x equals exactly negative 2. And we want to show 2 decimal places, 0.00, and of course x. So 62.93x minus 64.93x equals negative 2.00x. So now I just want to solve for x, and of course to get rid of this negative 2 I need to divide by negative 2 on the other side. So I've got to divide on both sides by negative 2, so x equals negative 1.38 over negative 2.00. My answer to 3 significant figures when I do negative 1.38 over negative 2.00 is negative 0.690. Not negative, I'm sorry, we just did negative over negative, so that is a positive number. 0.690 is x. Now, I have x. That is the abundance of copper 63. So this is copper 63. Copper 65, if you remember, is 1 minus x. Since it's 1 minus x, like we have over here, it's 1 minus 0.690 because we just found out that's what x is. So 1 minus 0.690 is going to be 0.310. 0.310. And then, of course, we need to turn it into a percent. So to turn these into percents, we need to multiply by 100 or move the decimal over 2 places. We're turning these into percents, so we need to make sure that we multiply by 100. So we end up with 69.0% copper 63 and 31.0% copper 65. And that's the answer that we were looking for in this problem. If that makes sense to you, go ahead and try the next example using the exact same technique. You can pause the video here and check your solution. You may have noticed, if you've paused the video and tried this out, that this problem is a little bit different. So let's look at a notable difference. As we read over it, it says magnesium 24 is its most abundant isotope, and it gives us this percent, which we didn't have in the other problem, and it gives us its exact mass. If the atomic mass of magnesium, so we have our atomic mass here, is 24.305 AMU, what are the percent abundances of magnesium 25? So we're looking for percent abundances of magnesium 25, which has a mass of 24.986, and magnesium 26, which has a mass of 25.983 AMU. All right, so a lot of information. Let's try to break it down in a table. So I'm going to start out by writing the symbol just to save a little bit of space. I'm going to write Mg24. I have magnesium 24. It's not the most common way of writing it, but you'll see this sometimes where they just put Mg and they dash and then 24, or we could even write it with the symbol with the mass number top right, or top left, I mean. So magnesium 24, and it gave us the abundance. Remember, the abundance is the percent written as a decimal, so we're going to change that to a decimal and make it 0.7870, right? And then we have the mass of that one is 23.985 AMU. Okay, the next thing that we see is, well, we've got our atomic mass. We'll come back to that. Then we have magnesium 25. It has a mass of 24.986. We don't know its abundance, so I'm going to call that X. And then we have magnesium 26, which has a mass of 25.983 AMU and an unknown abundance. That's what I'm looking for as X and Y. Remember that our abundances, all of our abundances, need to add up to equal 1, because an abundance is a percent turned into a decimal. So they all add up to be 100%, or we could say they all add up to be 1. So in this case, we know that 0.7870 plus X plus Y, so we've got 3 different numbers. Those all add up to equal 1. So if I wanted to figure out what Y was, I would need to subtract this. I would need to subtract this number and this number. Going to need to subtract both of them. Didn't mean to erase so many things there. sorry about that. And we will rewrite this. So to solve for y, I would say y equals 1 minus, well, first I'm subtracting 0.7870. And then I'm also going to say minus x. Well, I can't combine the x, but I can figure out what 1 minus 0.7870 is. That ends up being negative, or not negative, y equals 0.2130 minus x. So y 0.2130 minus x. This is definitely a more challenging problem. You don't see problems like this very often, but you do want to know how to solve them. So back to the way that we solved the last one. The difference is that number is a little different. So our atomic mass is 24.305 AMU. I've got that from right up here in the problem. Equals abundance times mass plus abundance times mass plus abundance times mass, just like in the last problem. So we're going to do our first abundance, which is 0.7870 times 23.985 plus x times 24.986, and then we're going to add that last factor, which is 0.2130 minus x multiplied by 25.983. And then we're going to distribute. Starting with this number staying the same, 24.305 equals, if we put 0.7870 times 23.985 in the calculator, I get 18.876, so 18.88 plus, and then 24.986x plus 0.2130 times 25.983. We've got to distribute. So again, we're distributing this number to this, and then we're also going to distribute that to multiply that by the x. So 0.2130 times 25.983 is 5.534. Minus 25.983x. Now we combine like terms. I know this looks like a whole lot, and it is. I'm going to combine like terms on the left first. 18.88 plus 5.534. And then I'm going to combine 24.986x minus 25.983x. So when you put that in a calculator, you get, write that again, we're going to get 24.305 5 equals 18.88 plus 5.534 is 24.41. And then we have minus, when you do 18.888 minus 25.983, I'm sorry, 24.986x minus 25.983x, you end up getting negative 0.997x. All right, finally, we want to combine these two terms. So we're going to subtract 24.305 minus 24.41. When you do that, you get negative 0.105. Which really just rounds up to 0.11, but we'll keep it there. That's fine. We'll round to 2 decimal places later. And you have negative 0.997x. If I were solving for this, I need to divide by negative 0.997x. What we end up with is 0.105. 0.105, which rounds to 0.11 based on the significant figures. Again, this really should have been rounded to 2 decimal places to be 0.11. So this ends up being 0.11. And as a percent, we would say that is 11%. Let's see, what was X? X was magnesium 25, so it's 11% magnesium 25. And if we wanted to find what Y was, well, Y equals 0.2130 minus X, which equals 0.2130 minus 0.11. It ends up being 0.10, which, as you know, is 10% written as a decimal. So it would be 10% magnesium 26. We could add them up and check our work. If I have 11% plus 10%, and that should be 10 with 1 decimal, with a decimal right at the end, plus the 78.7%, you end up with 99.7, which to significant figures is 100%. And in general, that's a good way to check your work with these, to add everything up and just see if you're at least very close to 100%. And that's pretty much it for isotope abundance. Try some practice problems and let me know if you have any questions.